And if you need to have a coworker watch it or anything like that, you can download it and watch it later. All right, so welcome. Today's topic, Controlling Hydronic Systems by Bill Shannell. Bill, I'll turn it over to you.
All right. Well, thank you. Thank you, Ryan. Thank you, everyone, for taking a little bit of time out of your busy day. I realize we're in the heating time of the season, and appreciate you doing that. What we're going to talk about today is, well, controlling hydronic systems is a pretty broad topic, and we could talk for days on a lot of this, but I'd like to focus in on primarily on residentially and maybe some light commercial stuff that you run into, and ways that we control systems to achieve the temperature and the comfort goals that we're trying to get. So along with that, we're having technical difficulties. That doesn't want to work.
Oh, there you go. Wasn't on the presentation.
There we go. There we go.
Okay. All good.
Residentially, really, there's two ways that we control to meet our goals of meeting temperature and comfort goals. One is by controlling the flow of the water out to the spaces that's bringing the heat. We can do that either with using pumps or using zone valves. Another way that we can do it is by controlling water temperature, where, again, we're either putting hotter or cooler water, depending upon where we are. Many cases, we're doing both of these things. We're using both of these to optimize the equipment that we have and to increase the efficiencies that we've got for the end user. When we're controlling water temperature, we're concerned about getting temperatures out to the space, but then also in many of our marketplaces that we've got, cast iron boilers are a very prevalent, very common product, and sometimes when we're running lower water temperatures, we have to protect the boiler because we don't want to have water coming back, return water getting much below 140 degrees, 135 degrees. So there's a couple of different ways that we do that where we want to protect the boiler. If we don't do that, we'll shorten the life of it, and the economics to the end user will not be good. So I'd like to start with that. So when we get into it, a hydronic system is just exactly that. It is a system, and there's more than just the boiler and valves and pumps and all that stuff. There's also the radiation. So I'd like to briefly talk a little bit about the different common types of radiation design that are out there, and some of the advantages, disadvantages, because you'll run into this, and these will come into play in also controlling it. So probably the most common residentially wise is a series loop where you just go out, piping goes out, goes through. Typically it's copper baseboard, and it just runs out, runs around the building, comes back, and you're good to go. You might see this in zones where you have one loop that's on the first floor, second loop on the second floor, one that's in the basement, that type of thing. So now the advantages to this is, if we get over there, is it's very simple, it's straightforward, it's inexpensive. You see these, that's part of the advantages to it. The disadvantages, and this is not, there we go. As that water goes through the system, you get uneven water temperatures. So it's going to start hot as it comes out of the boiler. If you look at that loop to the left, that first radiator off of the boiler is going to be very hot. By the time it gets all the way around the loop to the end, that water is going to be much cooler because it's given off much of its heat. Sometimes we can do a piping thing. I was out on a job just last week. They had a long series loop on the first floor. Suggestion was to put in, just like we have on the right, put a return in there halfway down. Now you're getting hotter water to the system. Also, you can build up a lot of resistance. If you get, for example, 3/4 inch copper fin baseboard is very typical. If you get beyond about 67 feet of that, your water temperature is getting cool, your resistance is getting higher. But many people didn't understand that, and they put 90, 100, 120 feet of baseboard all in one loop. You don't get good performance out of it. We can try to control it all you want, but again, If the design is not good, there's other things you can do. Another type of typical design, direct return. Here the hot water comes off the boiler, goes off through the pump, and goes into the first, well, here it's called terminal units, radiators, pick what you would like. Could be a loop as well. And then, the first radiator that comes off is the last one back. So it's the closest off of the boiler on the supply, and it's the closest on the return. So it's direct return. Okay? And the furthest loop is also got the longest run coming back. All right? Advantages, oh, here you go. Advantages. Again, here we get even water temperatures, which is good. We're not, and our pressure drop is better as well, because we only have to be able to pump the water through that furthest loop. Disadvantages, you get uneven flow. So that first loop is going to get a lot more water because it's the easiest path of resistance for the water. It'll tend to overheat that space, and the farthest one might not get as much flow. This is a higher cost to install than series loop, because you've got more piping, more fittings, that type of thing. But you'll see this type of system and the next one, a reverse return, you'll see a lot in apartment complexes and that type of thing. So speaking of that, reverse return. This is very similar to the direct return, except that in this case, the first loop, first one off of the supply, is the last one on the return. And you work your way through, and then, for example, the last loop off of the supply is the first one on the return. So again, we've got a lot of the same advantages that we had on the direct, where we've got supply water temperatures, lower pressure drops, and here we get even flow to the radiation, so we don't have to balance it as much. But again, we've got the higher cost. But that's these you will typically see in zone systems as well. Now, before the 50s and 60s and 70s, where we did a lot of series loop with with copper baseboard, before that, the very common method was using monoflows. Typically, you'll see this with cast iron radiation. You'll see in residences and that type of thing, where you'll have one big loop that runs around down in the basement, and then you'll tee off and go up to a radiator or a series of cast iron radiation. That's one of the advantages to this. It's very, very simple. You can do it. It's done very easily. But again, we run into uneven water temperatures, and this has some higher costs because the Mono-Flo Tees, which I'll talk about in just a second, are expensive, and they were expensive, but it was a very simple way to zone or to provide heat into spaces. And we can get into air issues because we're going up and down, up and down, up and down an awful lot. So we have to be aware of that. Okay, let's talk about a Mono-Flo Tee just real briefly. Mono-Flo Tee is like road construction. It causes a blockage. So if you take a look at that diagram down on the bottom, the water is off the main, it's flowing from left to right, and it runs into a cone that backs up the water. And it tends to block things up. And just like in traffic, what do we do when you get into traffic and things are all blocked up? Well, you start looking for other ways around it, and that's exactly what water does here. And so we're pushing the water ends up going up through the radiator and then joining back onto the main thoroughfare down below. Typically, you'll see this where you'll have one Mono-Flo Tee if the radiator is above the main, and you'll see two Mono-Flo Tees if the radiation is below, because you got to force hot water down and then back up again, or if you've got a real long loop or zone that's above the main. How you identify that is, again, you'll see a big circular system running through the basement, but you look for the T's and you will see a red ring or a red dot on it, and that indicates that you've got a monoflow fitting. So you see the red ring on there, the cast iron fittings sometimes had red rings, or the really old ones had a red dot on it. So you want to have that ring to the outside of the radiation. That indicates that the cone is pointing that direction. So if you've got the cone on the inlet side, you want it, for example, on the picture below, you want the ring on the left, so it tends to divert the water up through the radiator. If it's on the return, as we have it in this picture, you want the ring to the right, so it tends to be pulling. It's causing a blockage and pulling the water down. All right.
If anybody has any questions, if you want to type them in the box there, we'll try to go through them as we're going. So just type them in the question chat box, and I'll read them off to Bill as you guys type them in. Unless they're stupid questions, then I'll ignore them. No, I'm just kidding. I'll answer those ones later.
We'll cover them. We'll cover them all. The next one we see quite a bit. It's become very, very popular now. It's been around for many, many years, but we're starting to see it now, especially with the advent of high-efficiency condensing, modulated condensing boilers, where we are doing primary and secondary piping. And in this arrangement, we have a pump strictly for the boiler loop. It's called the primary loop. I like to call it the boiler loop. It makes it less confusing for people. So all that we're doing there is we're circulating water, making sure that we get the proper flow through the boiler and delivering hot water out to the secondary loop, or what I call the system loop, where we're circulating the water and getting it out to the radiation. Now we can do that using multiple pumps. We can do that with a single pump. We'll talk about that in just a minute. But there's a couple of things about this. It is easy to control the flow through your boiler. That's the main reason that we use it with high efficiency boilers, because we have to have the proper flow, get enough flow through those heat exchangers. So, and this is a great way to do multi-load systems. As you can see, it becomes simpler to add on additional zones. You can easily see this with, instead of 4 zones, you can see this with 16 zones. You just keep adding them up as you go along, and yeah, your pumps may or may not have to get bigger. So some of the disadvantages: it is a higher cost system, and you've got those piping requirements for the closely spaced tees. Let me talk a little bit more about that. This is very, very important. When back 10, 12 years ago, when the modulating condensing boilers started to come into play, this was the biggest issue that caused problems with those boilers. People were piping them just like they did a typical boiler, and they were not getting piped in a primary and secondary type setup where we had those closely spaced tees. It's absolutely critical that we do that, because that we get it within 4 times the pipe diameter. The reason for that is we want to isolate that loop, that boiler, hydraulically from the rest of the system, meaning the pump that's circulating the water for the boiler only has to overcome the resistance going through the boiler. The pumps that work the system loop, they're just worried about the system. And the closer we get those tees together, the better off that we are. All right? And it's become so important and such a prevalent issue now that many of the high-efficiency boilers that come out have the primary piping already internal inside the boiler. You'll see that in a number of the boilers that we have, or other methods of hydraulically isolating the boiler. So, did we have any questions that have?
We do. Fazil asks, most literature and guidelines suggest drawing through the boilers. What is the preferred piping schematic for a hot water system? So I'd ask you, Fazil, what do you mean by through the boilers? If you can clarify that for me, I'll try to get it answered.
Yeah. Yeah, that's.
Do you mean having the pump on the supply side of the boiler? Is that what you're asking? We say through the boilers. So, for example, on the drawing that Bill has up here, do you want the pump over here in that question? Right. So historically, the pumps have been on the return side. Okay, he said yes, that's the question. Historically, the pumps have been on the return side for a couple of reasons. One, it's easier to package it that way for the boiler manufacturer, who likes to supply the pump in many cases. And two, sometimes the pump seals didn't do so well with the hotter temperatures. So on the return side, if you're 20 degrees cooler, the seals might last a little bit longer. Nowadays, especially with condensing boilers, which is mainly when we're using this primary, secondary that Bill's talking about, the temperatures are already lower, so it's pretty much a non-issue there. And you can certainly put the pump on the supply side of the boiler.
Right.
Nothing wrong with that.
When people talk about pumping away, I'm going to go back one
Yeah.
screen here, if I can.
Yeah.
Let's see here. When people talk about pumping away, the critical thing here is that we want to be pumping away from the point of no pressure change, and that's where the expansion tank comes into the system. At that point, whether we're at 12 psi, 20 psi, whatever fill pressure that we filled to, it maintains and it stays static. So if we filled to 12 psi, for example, in a typical residential system, it will be the system will measure 12 psi at the point that the expansion tank is in the system. If we pump away from that point, as these pumps in the zones are showing, we are adding pressure. So all that a pump does is create a pressure differential. Say let's just pick a number, let's say 6 psi. The inlet side of that pump, if it was theoretically, if it was right next to the expansion tank, would be 12 psi. It would add 6 psi and make it 18. And it would slowly eat up that pressure as it goes through the system until the flow got all the way back to the expansion tank, and it'd be back to 12 psi. And then if we pump on the other side, if we pump into the expansion tank, we still make that differential, but we would have at the inlet side of the pump 6 psi instead of 12, which gets us close to being to the point where we can start to cavitate, where we'll start to get air separating out of the water inside the pump, or air will come out of suspension at various points inside the system. When we're adding, we're creating more pressure, we're keeping that air in suspension until we can get it to the air separator, which is the best place to get it out. So that's why we're talking about pumping away. That's typically we see that in the secondary loop. In the primary loop, there's a school of thought that says you want to pump into the boiler because you're giving the most amount of you're letting the pump eat up its pressure, pumping through the boiler. That might be where you were using the word through the boiler in a primary loop or a boiler loop setup. But again, as Ryan said, if we put it on the outlet side of the boiler, that's sufficient too. Again, we're working with that loop. Hopefully that answers that question.
Yeah. So I think in summary, on the secondary loop in this drawing, you don't want to pump into the expansion tank. It just chews up all your available pressure. And the pump's going to make, like Bill said, 6 psi differential. Why make it a negative 6 psi on the inlet side? Let's make it a positive 6 psi on the supply side.
Right.
If there's more questions on that, Fazil, hit us up later and we'll answer them for you as well.
Okay. Let's jump ahead a little bit. So now we get into zoning. Zoning with circulators. It looks familiar. That diagram kind of looks similar to the one that we had. And put a little picture on there. That's a pump salesman dream. It's got 15 circulators on it. So, but in that circumstance, what we have here, if you look at it, and again, remember the piping types that we had, this actually is a reverse return system where the first, and well, we'll take domestic water out of it, but the first circulator, the circulator number 2, is the first one that comes off the heat side, but it's the last one on the return side, so it's a direct return. Okay. Many times when you're looking at a building,
Reverse return.
I'm sorry, reverse return. I apologize. Many times when you're looking at a building, especially if it's a commercial building, apartment building, that type of thing, you won't know whether it's direct return or reverse return. And frankly, there's not a lot you can do about it once it's installed. So, but it's good to know if you can. It helps you with sizing the pumps at times. So, but what we've got here, circulating using the circulators to zone, became very popular in the 80s with the advent of the cartridge circulator. At that time, zone valves would be problematic, that type of thing. and the cost of those circulators came down quite a bit, and it became very much in vogue to zone using circulators, and that's pretty much continued through to this day. And so we see that. So now, when you've got these circulators, how do you turn them on? There's lots of ways to turn on pumps and turn on your boiler. On the left side of the screen, the RA32A, that Honeywell pump relay, which has been around for ever and ever and ever. It will take a call of heat from a thermostat or that type of thing, turn on a circulator, and also turn on the boiler. So one handles one zone, one pump, and one zone, and it'll turn on the boiler. If you have multiple zones, go back. If we look at the example that we had before, where we've got three heating zones, we'd have to have 3 of those RA32s on the wall. And once you do that, you start running out of wall space. You start having wires going all over the place. It gets a bit messy, but that's how it was done back before the advent of what's on the right side of the screen is the pump controllers or the pump relay panels. These are really, really nice. They make the job much cleaner. They give you the ability, many of them give you the ability that you can test the zones right from the panel itself. And they'll also give you, most of them will give you the ability to do domestic hot water, make it a priority. In other words, we want to turn on the loop and to get the hottest water into that indirect water heater to satisfy that before we worry about space heating. Somebody standing in the shower is going to notice a drop in temperature long before someone in a room sitting on the couch will notice a 1 or 2 degree difference there. So we want to take care of those folks first. With the old RA32s, you'd have to do some pretty tricky control wiring to do that. And here in the panels, it's integrated inside of them. One of the things I want to talk about are the Honeywell panels, the red and black ones that kind of look like Lego blocks. In there, we really like those. They bring some additional capabilities for us. One of them is their transformers that are in there. It's a 38 VA transformer. I think everybody's probably shorted out a transformer at some point by goofing up, crossing wires or something. You can't do that with these panels. If you directly jump out the low voltage or even the line voltage wiring on these transformers, they have an internal reset, and they just shut off and reset, and they're good to go. That's a huge thing for your technicians or even your service techs when they're trying to do something and they cross a pair of wires that they didn't mean to, and you smoke a transformer in a panel. It can get expensive in a hurry and embarrassing and all of that. Now with the Honeywell panels, they have basic ones, as you see on the top, and then as we go down to the bottom, you can get more and more features with all kind of reset and control and feedback and that type of thing. So let me talk a little bit about let's see here we go, unsynchronized controls. Now this could be a traditional pump panel. This could also be a series of RA32 relays. And the way that they call for heat is when they get a call for heat from a thermostat, they turn on, they tell the pump to run, they tell the boiler to run. When is a boiler most efficient? A boiler is most efficient when it's not running. When is it second most efficient? Is when it's at steady state. It's least efficient when it's starting or stopping. So what we've got here is, picture being in a restaurant. You got 4 people sitting at a table. Everybody's got a glass of water. You take a sip and you sip out of your water. The way this is set up is the waiter will run up and fill your glass of water immediately. Then Ryan takes a sip. The waiter's back again, fills his glass. Next person, each time somebody takes a sip, the waiter's running back and forth, running back and forth. It's not very efficient in the use of time. Okay. The way that the waiters typically do it is, I'll take a sip, then Ryan will take a sip, somebody else will take a sip. We'll have 3 or 4 glasses that are maybe half full, and then we'll come and fill up all the glasses. Well, what Honeywell's zone panels do is they have logic built into it to try to do the same thing. They call it zone synchronization. What we have here is we've got 3 zones, one running 20% of the time, 30% of the time, 60% of the time. But we actually end up running the burner and the boiler 90% of the time over that span. When we go to zone synchronization, what they'll do is they'll let a zone not come on. They'll wait a little bit before a zone comes on, or they'll run a zone a little bit longer to try to get them synchronized. So we have the same load demands, 20, 30, and 60%, but here we've got 2 cycles instead of 3, and we're running 60% of the time. We'll get some additional savings, 3 to 5%, they're saying. If you've got a system with a bunch of small zones, it can be dramatic. There have been some dramatic savings on this. This is one of the reasons why we like this panel. That's integrated in their basic panel all the way up to their high-end panels, and they're very price competitive with those panels. Let's see here. Do we have any other questions? Anything yet?
Nope, we don't have any questions right now, but if anybody has any, type them in and we'll answer them.
Don't hesitate to ask them. Okay. The next way that we go, instead of doing it with circulators, is we pump, or instead of using circulators, we're using zone valves. Again, similar design to what we had originally, but instead of having 3, circulator 2, 3, and 4 for those zones, we've got 1 heating circulator and then multiple zone valves that fit into this. This is a very common application as well. You'll see this residentially. As I said, back into the 70s and before, you'll also see this in a lot of commercial apartment type applications and that type of thing. Now, when we talk about zone valves, there's a couple of different types of zone valves. Okay, there's 2 basic types. One is thermostatic radiator valves. These are not powered. What they do is they sense temperature in the space, and they sense temperature that's that's going through the pipes, and they will modulate. There's a fluid in there. It used to be mercury, but they can't do that anymore. So it's an oil of some kind, I'm sure. But they will open and close based on what they're sensing at that bulb, and open and close a valve. So you'll see these a lot in, very often in systems that have cast iron radiators. You'll also see them in baseboard situations in apartments, complexes. Very common to see these things. So they'll open and close on those loops, and the demand of the flow of water will change as these zone valves open and close.
It's also a great retrofit, Bill. There's no wires involved, so it's easy to retrofit. Just mention you can't do it on series piping. You'll cut off the water flow to all the people after you.
Absolutely. That's one of the reasons why we want to know what is a system, what is the piping in the system. It's really good to know that, because it opens or closes options off, depending upon what type of piping you have.
We did have a question from Mike asking if the synchronization type controller is something that the utility rebates apply to. So there's no prescriptive rebate for it, Mike, which means that residentially you would not be able to get a rebate for a synchronization controller currently. However, commercially, as you're probably aware, if there's something that's not a prescriptive rebate, you can always do custom rebates. You probably wouldn't do it just for that panel, but if you're doing a bunch of stuff at that project to save energy as part of your project, it'd be one more thing that you would add into the energy cost estimate, and you would be able to get applicable rebate dollars as a result of that. So nothing residentially, yes, commercially, but it falls under the custom programs. And that would be true for all utilities in the Midwest area. All right, Bill, back to you.
Okay, cool. Let's get to the second type of zone valves. Anybody want to take a guess? I hope somebody would say electric. So this is by far, again, much more common. Here we got a White Rogers, a Taco, and a Honeywell zone valve. But basically, we're going from a thermostat that's mounted on a wall somewhere, and or some kind of a sensor that is telling us that we need heat or we do not need heat, and we're opening up the zone valve, and typically we're making an end switch. Some of these are easier to wire up than others. You'll see a lot of the White Rogers out there. You can see there's 6 terminals on there, and sometimes the wiring can be a little confusing for some folks. It can be a little challenging. TACO is only 3 wires, and more traditional and more typical zone valve is what you'll see there on the left, which is the Honeywell. And there you've got 2 wires that are used to tell the zone valve to open, and then there's another 2 wires that come off of that say that the zone valve is open. It's called an end switch, and that we turn on our piece of equipment. So now we got some wiring that comes into play. And just like we had with the RA32s, we've got the same kind of an issue here. As you can see on the left, it's a rat's nest, and especially since we're talking about different types of zone valves, these happen to be Honeywell or Honeywell-like zone valves. But since you can have all kinds of wires going all different directions, you can daisy chain them together. People got real creative back in the days. They got very creative in putting in their zone valves and controlling, telling the system to turn on and turn off. That's great, and it's a very inexpensive way to do it, but for the poor service tech that's got to come back and try to figure it out, especially when something's not working right, it's easy for things to go wrong. It's easy to miswire something. So again, we've got zone panels, but are just designed for zone valves rather than doing pumps. So they're looking for that. They're looking to make the zone valve open up, and then they're looking for that end switch to come back. Again, we've got basic panels. Again, I've got a picture of the TACO. There's other manufacturers that make it. And then there's the Honeywell panel as well. Again, Honeywell, even with their zone valve panels, we have that transformer protection. We have the zone synchronization, and that type of thing. So it is works out to be a very nice setup that way. Let's see here. Where are we going next? Overheating zones due to pump pressure. What we run into with zone valves, and this was an issue that they dealt with before circulators became the predominant way of zoning, was you would have a large circulator that's circulating that has to overcome the resistance for the biggest or the longest zone, and also be able to supply water in enough GPM to satisfy the entire system when it's open. And so what you'd end up with quite often was a large pump, which inevitably would be oversized, because
I'm shocked, Bill. I'm shocked.
Big is good, bigger is better, right? Not really. So what happens is, as zones close, and let's picture that the first 2 zones close, that third zone might be a very small zone. And so what happens is, one, if the zone valves are strong enough to stay closed against the pressure of the pump, you can overheat the pump. Sometimes you'll see, like the old 3-piece B&G pumps, the bearing assemblies will start to discolor. And what that's a typical sign of is you've got a small zone. We call it deadheading. It's essentially trying to push too much stuff through that small zone, and you're deadheading the pump. You'll burn up the pump. You're using too much energy. The amp draw goes up dramatically. The other thing that can happen is, if the pump is big enough, which can happen in apartments and condos and that type of thing, you can actually force open. You can push open zones that are closed, and now we're overheating. We've lost control of the system at that point. And so when you're doing zone valves, you have to be aware of this. With pumps, you don't have that big monster pump that's pushing water through it. So that was one of the advantages to go into that design. So now, how would we fix this problem? Well, there's a couple of things. One, size the pump appropriately. That typically would help. But another thing that can happen, and sometimes just the design, you're going to run into problems. There's an item called differential bypass valve. It's kind of like a relief valve. As zones close down and the static pressure builds up of that pump, this will open up and allow a bypass and flow water back to the return. These are expensive valves. You got to pipe them in, and you got to set them. And there's some trick to getting them set. So they're out there. You'll see them. It is a way to a solution to control the overheating issue. Another common way that they used to do was they would set up that bypass zone, or they'd set up a fourth zone and just put no control over it, and they just let the water run wild. It was called a wild loop. If you've ever walked into an apartment building, and you walk in typically, or a school or something like that, and you walk into an entryway, and you're going from outside temperatures of whatever, you walk inside and it's 80, 85, 90 degrees right inside the doorway. Chances are they've got a wild loop, and that's how they controlled their flow issue. They let that one space overheat, let it be uncontrolled, so that they had better control over the rest of the loops. Again, if you've got that, that's fine. People have been living that way for decades. But there's better ways to do things. That's a nice design from the 1930s, But we're in the 2010s and the 20-teens. So how would we maybe do this a little bit better? Do we have any? Okay. Okay. So there we go. Better solution. Better solution is better technology. Grundfos has a series of circulators, other manufacturers do too, that are basically variable speed circulators. They're like an ECM drive on a furnace. They vary their speed based on the load that's presented to them. First of all, they're much more efficient. That pump on the left side, the alpha pump, is very similar to, in its performance characteristics, to the B&G Series 100, the traditional three-piece pump there's 500,000 of them out there. The Series 100 is an on-off pump and runs at 200 watts. That alpha, at full speed, running whatever to the walls, is using 45 watts. So it starts out, initially, is much more efficient. Then it has the ability to slow down as the need requires. So as zones close down and you don't need as much flow, it will actually slow down a little bit. Then you go over to its big brother, the Magna 3. It has those capabilities. Well, let me put it this way. Magna 3 is kind of like having a pump, a variable frequency drive, and a computer all together in one place. It has the ability, again, it's a highly efficient pump. It's an ECM-driven pump, but it can do a number of different things. If you want to have a constant flow because of your design, let's say you want to have 22 GPM at all times, it will give you 22 GPM, and it'll ramp up or slow down depending on as the need demands. There's no need for balancing valves, circuit setters, flow control you might need, but other things. It has a temperature sensor built into it. You see that wiring hanging off the bottom. You can provide a constant temperature of water if you want to. It will interface with building management systems. There's a card. You just have to identify the management system, plug the card in. I mentioned the computer. It will report on its energy use, tell you how often it's been running. If there's redundant pumps, they will communicate to each other via Bluetooth. And if one, they will lead lag. They'll turn each other on and off. Or if one, for some reason, stops working, the other one will know and pick up the load. So again, there's a lot of intelligence built into these, and they're also controllable from your smartphone. You can control them as well. These are the most efficient pumps that are in the world today. Again, there's a better way to solve that control problem, that water problem. Okay. So let's go one more. And with the advent of these circulators, zoning with zone valves is going to come back. So again, I go back to that picture where you got 15 pumps. And I'd love to sell the 15 pumps. That would be great. But each of those pumps is probably running at 90 watts. So here, if you go 15 zones at 90 watts, you're running 1,350 watts. Magna 3 maxed out in this application is probably going to be in the neighborhood of 400 watts. You're saving 950 watts, or nearly 16 60-watt light bulbs. This is where our next level of efficiency savings is going to come from. It's actually going to be on the electrical side as we go along. If you're doing LEED, you're looking at LEED certification or trying to get a LEED building, you're going to be looking at these very intelligent pumps. in conjunction with zone valves, whether they be, these ones are larger zone valves. That's where the design is going to be going in the next few years to 5 years. We're going to start to see that a lot more.
It's also an installed cost, Bill, because obviously all those pumps require 120 volts, whereas zone valves typically are low voltage. So it should be a install cost savings for having a singular pump versus many pumps.
That is correct. That is correct, as well as the control capabilities of interfacing with a building management system. There's a lot of advantages to it as we brought the intelligence into that. So, do we have any good questions at this point? Okay. So that kind of covers the flow side of things. Now let's talk about temperatures. Okay. And first and foremost, when we're talking about controlling water temperature to supply to the zones, we're looking at outdoor reset. I got a couple pictures there of the typical reset panels. One's the Techmar panel. Again, Honeywell's got a reset panel that we like as well. So we'll talk about that in a second. But what we're doing with outside or outdoor air reset is, and here's a picture of a curve where, if you look at it, when we're at 60 degrees outside, for example, in this particular curve, when it's 60 degrees outside, we turn on the boiler and we're going to supply water at 120 degrees. So, and as we're at 0 degrees, we're going to let the boiler run all the way up to 180. So what we're doing is we're controlling the limit that the boiler has based on outside air temperature. In this circumstance, we clearly have a condensing boiler because we're running water temperatures down in the 120s. If we've got a cast iron boiler, our low end would be sitting at 140. We'd be looking at, or actually 150 probably, to keep the water temperatures above condensing. But again, outdoor reset works very well with a cast iron boiler as well. But here we're just trying to match the load requirement, how fast the heat loss is going up, and satisfy it with the lowest temperature water that we can. And so that's the concept of outdoor reset. Again, here's just another descriptive. At 10 degrees, our set point or our limit on the boiler is 140. As the temperatures drop, it goes up to 180. As the temperatures rise, it goes up to 120. Very common inside of outdoor reset controllers is the ability to do what they call warm weather shutdown. So you set a point at which you turn off the boiler. That's great unless you're doing indirect water heating. If you've got an indirect water heater, you don't want to shut the boiler off. You don't want the boiler to be shut off when you're at 75 degrees and somebody wants to take a shower. They're going to want hot water. Well, you don't want the boiler to be shut off. We'll talk about that in just a second. So here's another example of a situation where we are doing outdoor reset. And we've got a sensor out there. How can we improve upon outdoor reset? That's one of the things. Outdoor reset's been out now for many, many, many years. You can save anywhere from 7 to 15% using outdoor reset. But is there a way to improve comfort, to improve control a little bit? Well, Honeywell's come up with a way using their panels. You look at this situation, we've got a zone that satisfies in 5 minutes with a boiler temperature of 110. We've got another zone that, be it larger, be it that they've got a leaky window, be it that they've got a bunch of windows that are facing north, whatever the reason is, that zone takes a lot longer to satisfy, running at the limit that's created by the outdoor reset. So to make it a little bit more comfortable, Honeywell uses what they call, or has available, what we call load reset, which once the other zones are satisfied, it'll actually raise the limit on the boiler to satisfy that one zone that's a problem. So in this case, we jump from 110 up to 140. We decrease the amount of time. We keep the comfort in that zone. Is it more efficient, less efficient? I don't know. It's kind of a trade-off. You're still going to put the BTUs into the space, but you're not going to have as great of a temperature swing. And your consumer, your end user, is going to end up with a lot more comfort. They're going to be happier. And then once that call is satisfied, it goes back to the original reset. So that's integrated with all of the outdoor reset panels that Honeywell has, whether they're zone valve or whether they are pump panels or even their outdoor reset panel. Also, the Honeywell outdoor reset panel gives you the ability to do priority for domestic water, as we have in this example. Now to do load reset, we need to use their communicating thermostats. They're not very expensive, but you do need to use their programmable or non-programmable thermostats. That's one requirement that's needed.
So that zoning panel could be used with or without those stats, but if you want this feature, you need to use these stats.
Correct. Yeah. Let me go back over that. Make sure that those panels can be used with any thermostat. But if you want the load reset feature, if you think you're going to have a situation where you've got that, you will need to use their thermostats with that, their AQ series thermostats. Interestingly, these same thermostats will also sense either a slab. You can use a slab heat, so you're sensing the slab if it's a radiant zone, or air, or both. There's a lot of functionality to these thermostats that can be used.
Bruce does ask a question. So can you add the outsider reset temperature 120 example and know exactly what the water temperature should be? Yeah, Bruce, on the outsider reset schedules, you're determining what those schedules are. So if we went back a few pages on Bill's drawing over here, I get to pick what these points are. I get to pick the 60 and 120 and the 0 and 180 in this case. And I could pick something else if I prefer, right? And then all those curves are known values then. So I can know on this particular one, if it's 30 degrees outside, I'm going to have 150 degree water temperature, right? So if I pick the starting and stopping points of the curve, I know if you tell me the outside air temperature, I can tell you exactly what supply water temperature I should be at for that particular scenario in that moment in time. Hopefully that answers your question, Bruce. Bob, we also saw your question, which is specific to a specific boiler manufacturer's reset panel. So I will get with that manufacturer's rep, and I will get you that answer, Bob.
Okay. Cool. Good stuff. Thanks, guys. It's great getting feedback like this and good questions. All right. Next way that we can control water temperatures, mixing valves, the old tried and true. And there's a couple of different types, three-way mixing valves, four-way mixing valves. Three-way mixing valves, they are inexpensive. They're simple. They're straightforward. They do a great job. One thing is they control temperature going one way. So if we've got a cast iron boiler, we have to be aware that we might have cold water temperatures coming back. It does not protect that boiler. So I talked about protecting the boiler. If it's a cast iron, with three-way mixing valves, you have to be aware of that and maybe make some kind of a provision for it. However, if we've got a condensing boiler, we want low water temperatures coming back. The lower the water temperature, the better. Man, those things eat them up and chew them up, and they're much more efficient with lower water temperatures. So three-way mixing valves are our friends when we're talking about condensing boilers. Another mixing valve is four-way mixing valves. Those will mix in two different directions. We'll get the low temperature down to the space that we want, but we'll also be able to get a little bit higher temperature back to protect the boiler. This is a very common way when we've got cast iron boilers in radiant applications. Back before we got into the condensing marketplace, we saw a lot of these. You'll see these out on jobs from time to time. They can be either manually set or driven with an actuator. If they're manually set, they're going to do an okay job of mixing the water, but they won't adjust as conditions change. Obviously, if they've got an actuator on there, they're reacting to temperatures and that type of thing. They do protect the boiler, which is great. Disadvantages, they can be expensive, especially as you get into bigger sizes. One thing, if you are designing a system that's going to use four-way mixing valves, quite often you can size the mixing valve smaller than the piping that you're running, because you can size it based on the load that's out there. Quite often we'll see four-way mixing valves that are 2-inch or 1.5 inches, when in fact they really could have been 3/4 inch or 1 inch. Big difference in cost. So you want to take a look at that.
You also get better controllability with the smaller valve size. The valves don't do a very good job in general of controlling at the small range. So if you make them smaller, then you're controlling at the big range of the small valve.
Right. Now, if we want to get to precise control, there's another way of providing temperature to a zone, and that's through injection pumping. And that's where we're using logic out of an injection pumping panel. As you can see there, we've got a boiler loop, we've got our low temperature loop, but then we've got a couple of pipes. We've got a supply and return that's feeding the water into that low temperature loop. We've got a pump in there, and then on the return side we've got a valve, a balancing valve, a ball valve, globe valve, something that we can provide some load, that pump that's on the supply side into the low temperature loop can pump against. And what we do is we measure the temperature of our that's in the low temp loop, and we either speed up or slow down the pump, the injection pump. That's the logic that's built into these controllers, and they'll do that. These are used, again, we saw a lot of these go in when we're using cast iron boilers, again with radiant loops. We're concerned about return water temperature to the boiler. There's a sensor that goes on the return that goes back to the boiler. We make sure that the boiler has at least 140 degree water return. We would see that. We also see these when temperature control, the temperature that we want in this secondary loop is very critical, that we maintain a certain, within a certain temperature range for whatever reason, whether we're in a staple up, we don't want to dry out wood or slab or something like that, or some other application.
Yeah, process application.
Could be a process application, exactly. The third place where we would use injection pumping is it's a great way to get hot water to a very far away place. So figure you've got a warehouse that's how many hundreds of thousands of square feet, and you have a loop that's at the far end from where the boiler is located. By using injection pumping, we can use relatively small pipe sizes to get the water. We can use it as a distribution method to get that hot water out to the loop where we want the heat. Again, we can control that water, but we can do it effectively, very effectively, and very cost effectively. So you'll see that in those scenarios. Quite often those pumps are just a regular pump. Could be regular, Grundfos 1558 or a 1542, depending on the size. So, but it's controlled through the voltage from the panel. All right. And then when we're talking about protecting the boiler, the old standby, again, cast iron boiler, you'll see this in a lot of residential applications, especially if you've got large radiation. The installers would just put a ball valve or a globe valve on either the supply or the return, and then on a bypass, and just play with the valves until they get the water temperature protecting the boiler. Very simple way of doing it, very cheap, but it doesn't change as the boiler changes, as the conditions change, and you are always circulating some of your heated water back into the boiler. Even when you're at full load, you're still taking some of that capacity of the boiler and putting it right back into the boiler. So it's the least efficient of the options, but it's the simplest, and it does work typically. So that's another way of doing it. We are running short on time, but I wanted to go and see if we have any additional questions.
Fazal has a question. Can we reset the water temperature from the 3- or 4-way mixing valve? I'm assuming you mean reset it automatically, Fazal, as opposed to manually. That's probably what he's asking, I'm thinking.
Yeah. Yes. Okay. So we're looking at that for can we reset them? Yes, there are 3-way and 4-way mixing valves that can be that have actuators that you can adjust, and you can control what your outlet temperature is. Absolutely, yes, you can do that.
So normally these ones would be manual things, but you can do, like Bill had mentioned, wired ones, and then you can put them on some kind of reset schedule.
Correct.
Anybody else have any other questions they want to type in? We'll hang out for a couple minutes here if anybody does, and we'll try to answer them. All right, so Michael asked the question, what temperature should we keep on a cast iron 80% residential boiler, 140 degrees or 180 degrees, or something else, obviously?
Well, what we want to make sure on a cast iron boiler is that our return water temperature is at least 140 degrees. What is our supply temperature or our limit that we're operating on? that can vary depending upon what you're heating. If you're running, typically if you're running cast iron baseboard or excuse me, copper baseboard or fan coils or that type of thing, you're usually supplying higher water temperatures, so you might be 180, 190 degrees. If you're going to cast iron radiators, 180 degree cast iron radiator is really, really hot, and people are going to burn themselves. So typically we see lower supply temperatures there. But it kind of depends upon what the load is. But what we want to do is we want to have our return water at about 140 degrees or so it protects the boilers.
Yeah, so like Bill mentioned, normally systems are designed for 180 traditionally, and normally they're sized for a 20-degree delta T on the radiators traditionally. So that means you usually have a 160 return. If you're trying to keep 140 or so at the return, you're probably only be able to reset the supply water from 160 to 180 or maybe 150 to 180. That's kind of your maximum reset. Whereas a condensing boiler, I can reset it from, hell, I don't care, 50 degrees to 180 if I want to. But for a cast iron, you're resetting between 150 or 160 as your low, 180 as your high. Michael also asks, notice that all the Honeywell L-Series Aquastat at standard 180-degree limit.
Correct. That's very typical. That's a very typical limit that's set on cast iron boilers, where they want the boiler to shut off if the water temperature inside of it gets up to 180 degrees. That doesn't mean that that's the right temperature for your system. It might change. You might need some extra output, when it's cold, so you might bump it up, or you might bump it down depending on what kind of heat emitters you have. So
you're probably never going to put it up above 190 because at some point you'll start inadvertently making steam, depending on the pressures. But if 180 is satisfying everything, and you want to try 170 or 175, and you don't have an outside air reset control, feel free to try 170 and see if you can keep the building maintaining temperature. If you can, in most cases you probably can because the boiler's oversized, go ahead and do it and save that energy.
Right. Exactly. Let the system, let the pump circulate the heat that you put into the water circulate, and we don't need to put any more energy into it than we need to. So.
All right, I think we're going to go ahead and close it down. We do owe an answer to Bob. We will get that to him. But for everybody else, thank you guys for logging in, and we will see you guys next week. Next week's topic on Monday is I'm drawing a blank. Domestic water heating, a tank versus tankless discussion. Right? There's obviously a lot of interest in tankless these days, but there's still a lot of advancements in the tanked world. So we're going to debate both of those topics with each other. Additionally, if you're interested, there is actually a special webinar that we have added, which is on this week, November 6th. We're doing it in conjunction with the Indiana chapter of ASHRAE, but anybody's welcome to join us. The topic on the November 6th is gas detection and control systems. So those are the next ones coming up, as you can see hopefully on the screen there, what we got going on. And if you have any other questions, feel free to email us or give us a phone call. Thanks, guys. Bye.